Let's take a look at a couple half-life problems. Back in Algebra 2, remember your formula was the good old PERT formula. And what we've done with that is change that to C equals K to the T. And we know that K, actually, if we were to do a little analysis on this, we could actually solve for K and write it as negative natural log of 2 divided by H, where H is defined by our half-life. Okay. That could be solved, if you wanted to solve the equation, that would be 1/2 of P equals the initial P times e to the k t, and solving for that would give you this setup. Okay. We know that this is based upon the population being proportional, the rate of change of population being directly proportional to the amount that's there. And we even have one that's a very common one, and that's carbon 14's half-life. It's 5,730 years. The next one, or this particular problem we're going to do using this information, is with radium-226, which has a half-life of 1,590 years. How long will it take to reduce 100 milligrams to 30 milligrams? So we know, based upon what we've done up above, that whatever amount we have, P of T, will be the initial 100 milligrams times E, and in this case, our half-life, our K, will use our half-life, the natural log of 2, divided by the half-life of 1,590, and we're going to solve for T. Okay, I'm sorry, I need to set that equal to 30, don't I? Not the initial one. So let's go ahead and solve for T by setting that equal to 30. Divide both sides by 100. Negative natural log of 2 divided by 1,590 times T will equal 0.3. Take the natural log of both sides. The natural log of 2 divided by 1,590 times T will equal the natural log of 0.3. Going ahead and solving for T, T would equal the natural log of 0.3 times 1,590 divided by negative natural log of 2. If you were able to successfully put that in your calculator, you'll get 2,761.770 years will be how long it would take radium-226 to get to 30 milligrams. Next one is, our next topic is the Newton's law of cooling. And Newton's law of cooling is not directly proportional to the temperature, but the rate of change is proportional to the difference between the temperature of the object and the surrounding temperature, T sub 0. Okay? So in other words, the rate of change of the temperature, D capital T, D lowercase t, capital T for temperature, lowercase t for time, proportional to the difference between those, the temperature of the object minus the temperature of the surrounding area. Okay? So another way of this is actually shown is when we solve this, you can see this is separable. I can divide both sides by T and get 1 over T minus the surrounding temperature times D capital T would equal K times lowercase t. We've separated our variables. We can integrate this with a lot of fun, and we'll get Newton's law of cooling, which says the natural log of the absolute value of this. Okay, I do want to remind you, T sub s is going to be a constant. Okay, when we apply this, we're assuming that the temperature isn't affected by whatever we put in there. So that's going to stay constant. So T sub s is a constant. And you'll see that this will be a k times t, our time, plus some other constant. So let's use that to solve this problem here. Usually what I like to do on these is go ahead and set up a table of values based upon what they give me, comparing T and capital T. If the room temperature is 60 degrees Fahrenheit, that's telling us the surrounding temperature, T sub S, is 60 degrees Fahrenheit. And if coffee cools from 100 degrees at the beginning, when T is 0, to 90 degrees in 10 minutes at T equals 10, how long will it take to get to 80 degrees? It kind of gives me everything in a nice, concise way. So the first thing I want to do is solve for C, putting in this initial condition here first. So let's do this guy first. That will give us the natural log of the 100 degree coffee with the surrounding of temperature of 60 degrees. That's going to equal K times 0 plus C. So that tells us that C equals the natural log of 40. Next, we'll use this information to solve for K. We know that the natural log of now the new temperature is 90 minus 60 will equal that time of 10 minutes times K plus our C of the natural log of 40. Subtract the natural log of 40 from both sides and then divide by 10. I'm running out of room, so you can easily do that. Natural log, this would be the natural log of 30 divided by the natural log of 40, and then we're going to divide this by 10. That gives me my K, which means now I'm going to solve for T using this piece of information here. So again, running out of room, just write this as small as possible. This will be 80 minus 60 equals that K value we got here, the natural log of 30 divided by the natural log of 40 divided by 10. That is times T, and then plus the natural log of 40 that we had before. Okay. Should be a 40 there. It looks like I just wrote 4. All right, so you can do this on your calculator. Subtract the natural log of 40 from both sides, and then multiply by the reciprocal here, and we should get a time of 24.094 minutes. Okay. Next one says, again, we have a surrounding temperature of 40 degrees. 65 degrees. The orange juice is taken out of the 40 degree refrigerator, therefore it should be at time T equals 0, 40 degrees. And 1 hour later, or 60 minutes later, we're at 50 degrees. It says what will be the temperature after, what will be the temperature after 3 hours, or 180 minutes. So let's do the same thing we've done on the last one. We'll start out here with our initial conditions. That'll be the natural log of the 40 degree orange juice minus the 65 degree surrounding temperature. That's going to be 0, or K times 0 plus C, so C will equal the natural log of 15. Next, we'll use this information here, the natural log of the 50 degree orange juice minus 65, the surrounding temperature, at time T equals 60 times K plus the constant of 15 is going to give us the value of K. So you'll see with this one, I'm just looking here and my math looks a little bit off. I'm sure you guys caught that. 40 minus 65 is actually 25. So this should be a 25 rather than 15, because I should get 15 here. The natural log of 15 minus the natural log of 25, all divided by 60, is what k will equal. Now let's go ahead and find out our T, that temperature after 3 hours. The natural log of whatever that temperature is minus 65 will equal 180 times this thing here, k. The natural log of 15 minus the natural log of 25, all divided by 60. That's the k.